so we simplify radicals of any degree the same way we did when we simplified, or I guess I should, oh my gosh. We simplify radical expressions the same way we did for this unit as we did in the quadratics unit. The only difference from what we are going to do here from there is that everything was always a squared index in the quadratics unit. Today, in this unit, we have other degrees. We might have a third, or a fifth root, or a sixth root. So that's what we're going to have to pay attention to. But the process is still the same, and it's still, that radical still isn't in simplest form until there are no perfect nth powers of whatever that degree is of your radical left underneath there. So let's just go ahead and look at number 10. So the cube root of 104. You guys can check to see if 104 is divisible by any of those perfect cubes, those cubes being one cubed, which we don't really include when we're trying to simplify things, and then 2 cubed, that would be 8, 3 cubed, 4 cubed, 5 cubed. So is 104 divisible by any of those cubes? And it is. 104 is just 8 times 13. So if you guys are able to figure out what perfect cube is divisible by, you can factor that out and say then the cubed root of 8 is 2, and that cubed root of 13 will stay underneath there. However, if you're trying to do this without a calculator, I think the easiest way is by factoring. And then we'll talk about sort of how we figure out what perfect cubes are in there. So if we just make a factor tree, 104, even number divisible by 2, so 2 and 52. 52 would be 26 and 2. 26 would be 13 and 2. So whatever your index or your root is what you're trying to find a group of. So if we have a cubed root, let's cross out the numbers we factored out because we're only interested in the prime numbers at the end of the branches. If it's a cubed root, we need a group of 3 things that are the same. And in this case, that would be your group of 3 2's. What is 2 times 2 times 2? 8. That's your perfect cube value. But because we found in groups of 2, we know that's the number to pull out. So that group is what comes outside, and anything left not within a group of 3 things is going to stay underneath your radical. So it doesn't matter how you get there, but you need to make sure that you can identify those perfect cubes within that number to simplify it. So let's go ahead. I'm going to jump around a little bit here and look at number 16. So some of you guys might be noticing that 625 is a perfect 4th root, and it is 5. But for the sake of factoring, like we just did and learning that process, let's factor 625. So let's see, 5 and 125, 25 and 5, 5 and 5. So cross out, you don't need to, those ones that are not prime numbers. So since we have a 4th root, we need a group of 4 things alike. And because this is a perfect 4th root, there's nothing left to stay underneath that radical. So the 4th root of 625 is 5, but what about z to the 12th? How do we take the 4th root of z to the 12th? Well, you could write out the factored form of that. The factored form of z to the 12th is 12 z's multiplied together. So you could write out 12 z's and find groups of 4 of them. 1, 2, 3. It would be z to the 3rd because there's 3 groups. We also know how to rewrite this in exponential form. If we took the 4th root of z to the 12th, it would be z to what power? 4/12 or 12/4? 12/4, which equals z to the third. So in this case, this is a perfect root for both the number and the variable. 625 has a perfect fourth root. Z to the 12th has a perfect fourth root. So let's go ahead and look at two more here. So let's look at 20 and then 17. So the cubed root of 6x to the 4th, y to the 9th, z to the 14th. So you can't take the cubed root of 6. So since you can't take, I mean, it would just be like 2 times 3. There's no perfect cube root in there. That 6 is just going to stay underneath there. Okay, so what about the cube root of x to the 4th? How many times does 3 go into 4? 4 divided by 3? 1 time with 1 remaining. What about y to the 9th? 9 divided by 3 is 3. No remaining, so that will stay. And then z to the 14th. 3 goes into 14. 4 times it would be 12. So there would be 2 remaining. So if they aren't a perfect root, then there will be items underneath, values underneath that radical, whatever the root might be. Okay, so 17 is not a radical or a root, but because we know how to go back and forth between the two, how could we rewrite the whole thing, 32 m to the 5th times n to the 30th, all to the 1/5 power, in root form? Well, it would be the 5th root of all of that, right? 32 m to the 5th n to the 30th. And we could put it to the first power, but anything to the first power is really just itself. So it would just be the same thing. But now we can take the 5th root of everything like we've been doing. So 5th root of 32, you could factor it, but the 5th root of 32 is just 2. 5th root of m to the 5th would be m to the 1st. 5th root of n to the 30th, 30 divided by 5 is 6. Another perfect root here to simplify. So whether it be numbers or variables, you can always put it into factored form, whether with a factor tree, writing out the variables, and find those groups of whatever your index is, whatever that root is. But if you know what the perfect roots are, you could do it that way also. You just need to make sure it's completely simplified.